Maybe we should talk last few minutes about fine-tuning.
Yes.
Because when I was presented with this idea to have this discussion, I thought it was a very interesting idea to think about it, and I'm wondering what your views on after you gave it some thought for your presentation.
So I have to admit that as an observational astronomer in my day-to-day life, I try to avoid thinking about fine-tuning as much as I possibly can. But that's partially because obviously it is something that as astrophysicists we are uncomfortable with, we are trained to be uncomfortable with. If you ask me whether in our field issues of fine-tuning arise frequently, I would say yes and no at the same time. So yes, in the sense that, as I mentioned earlier, we are studying intrinsically complex systems, and therefore the particular set of properties that any system displays are likely to be, in one respect or another, fine-tuned. But no, in the sense that my overwhelming feeling from the 20 to 25 years of exploring planetary systems is that so far, pretty much every possible kind of planetary system that can exist has been found within the limits of what we're able to find currently. And in fact, that was a question.
Pulsars.
Even around pulsars, exactly. And one of the questions I actually had for you is whether in the last 30 years of progress in our understanding of planet formation, we have identified kinds of planetary systems that really should not exist.
I don't think so, but I'd have to think more deeply about the question. My gut reaction is no, for all the reasons you mentioned. We found such a diversity of planetary systems. I also agree with your statement about complexity and what I like to think of as filling of phase space. It's just completely packed and full. Everything that can exist does. And that gives me hope, it gives me optimism. I think there's lots of opportunities in that parameter space to realize every possible thing that could happen. So I'm not so myself enamored with the idea of fine-tuning in this context. Things that can't exist from general notions of planet formation, I think we run the risk of finding, planet formation is incredibly complex itself, and the outcomes are complex. And that to me is a little bit scary because I worry if I focus too much on a fine detail that I'm studying the weather and I'm trying to predict the weather, and I think that that's a fool's errand. What I hope we can do is to focus on climate. So we can tell stories, we can constrain climate, but we shan't spend our days trying to predict the temperature, at the corner of one street and another. And I'm always constantly looking in our models of planet formation for organizing principles that will give us pathways to certain classes of systems. Yes. And that is one thing a colleague of ours, Alessandro Morbidelli, has highlighted in his, he spent much of his career fine-tuning a model for the formation of the solar system, and he's well aware that is a very, very specialized model for our own solar system, the Grand Tack, where Jupiter and Saturn also migrate into the inner solar system and disrupt the embryos of forming planets, and then come out again at just the right moment to preserve the formation of the Earth and Venus, but allow Mars to have the small mass that it has, where dynamical simulations would predict that if there were enough rocks there to form planets, you should have a larger Mars. That story of how special our system is told in a context of, is the innermost giant planet bigger or smaller than the second one? And that is a key question for the dynamics. If the inner one had been smaller than the outer one, the story would be different. And for Alessandro, that's a kind of a pathway. There are dynamical trajectories for what that mass ratio is of the one that's closer to the ice line and the one that's farther out. And that to me is a very interesting way of looking at it, because it tells a story about which way, and different flavors of planet formation, or planetary architectures I should say, which way they can end up. And I think that's the way we need to find these organizing principles about what the formation processes are and then what the outcomes are.
Well, yeah, I mean, I find the whole Grand Tack model both fascinating and somewhat unsatisfactory because it is so specialized and so complex to explain just the one system. I would like to see investigations along the lines of in what fraction of planetary systems would such an event be likely to occur, and what does it depend on? What are the critical parameters, such as the ratio of the masses of the two giant planets, etc., etc. It has to be said that we often compare the demographics of planets that we find to the predictions of models of planet formation, these so-called planet population synthesis models, and that is a very difficult thing, because I haven't yet come up with whether it's real or invented, I haven't yet come up with a population of planets that could not be reproduced by suitably fine-tuning the parameters of the model that forms the planets.
I have a love-hate relationship with the population synthesis models, and to define what that is, that's our colleagues take everything that we think we know about planet formation and try to parameterize it as best they can, and then sample over distribution functions of initial conditions, and then just hope for the best and let the computer predict an outcome. But as you say, there are many knobs in those predictions. I think they've been useful to help guide us, but at the same time they are strongly biased and informed by the data, the outcomes of the data, but also the inputs of the initial conditions. I think we've made a lot of progress in helping them understand the ranges of initial conditions that make sense, but I'm also worried because there are very important variables like migration and the way in which gas and planets interact to move the planets around in those forming planetary disks. These are really not well understood processes yet, so there is a lot of freedom in making those models fit. I would prefer that we stick with the data for now and try to really understand the demographics, as you said before, from a non-parametric biased viewpoint. Try to understand the global population, and then we'll still keep making baby steps to understanding the processes as best we can.
But it's very interesting, because when you propose, as an observer, if you propose a survey, theorists who are assessing the proposal will tell you what theoretical questions are you going to answer about how planets form and evolve. And if you just say, well, I'm going to explore this region of parameter space, which has never been explored before, typically that argument is not considered sufficient. It's considered interesting and important, but they also, and I think they have a point, they will say, we want you to try and address specific scientific questions, that we at least want you to be able to formulate them and explain to what extent you will or will not be able to answer these questions with the survey you're proposing.
And I absolutely agree. Myself, as a proposal writer, those are always the most successful experiments to propose, and trying to train a student that, yes, indeed, this is the way we can make progress faster if you have a robust astrophysical theory that you can test that can be falsified, right? This is, again, the central tenet of the way in which we conduct the scientific method. But you're also right that exploration is very, very important. I just think it's particularly good if we can label it as such when we do it. There's nothing wrong with exploration. It's really something if we had more resources, we'd be more open to doing more exploration, because it's really the way forward, because it doesn't include all of our biases about what the outcomes should be. On the other hand, making rapid progress in falsifying theories is really what we are trained to do as scientists.
Exactly.